Hello and welcome to today's session. What we'll look at today is a quantum phenomena question. So we'll look at two of them. And as we know, paper 1 is 26th of May, paper 2, 10th of June, and paper 3 is the 16th of June. So the two questions we'll look at, one will be on the photoelectric effect and the other one will be on wave-particle duality. Just a quick recap of the photoelectric effect. You have a photon with frequency, at least the threshold frequency, that's incident on a metal surface that interacts with an electron. So you have a one-to-one interaction and then an electron is emitted. And we can think of this in terms of a potential well where these electrons are trapped and the work function is the energy required to liberate an electron. In terms of the equations we're using, we've got this section from your formula sheet, photons and energy levels, so the photoelectricity effect, that equation here, noting that the kinetic energy max can also be in terms of the stopping potential, so you can apply a stopping potential to stop the electrons being emitted. So a particular voltage is applied, so the EK max can be written as half mv squared, or it can be written as q times v, so the charge of the electron multiplied by the stopping potential. So just be aware that this term can be written in these two forms. The other thing that you'll have to do most of the time is use electron volts. So 1 eV, 1 electron volt, is equal to 1.6 times 10 to the minus 19 joules. Okay, so the question we have then, we've got a plate of zinc is illuminated by electromagnetic radiation of wavelength 2.1 times 10 to the minus 7 meters. The work function of zinc is 4.3 electron volts. Calculate the maximum kinetic energy of a photoelectron. So we've got our relationship here. We've got the photoelectric effect formula, and we're given the incident photon wavelength. So we can use this. We can write photon we can write our formula out. So HF is equal to phi plus EK max. Because we're given the wavelength, we can rewrite it as HC over lambda is equal to phi plus EK max. So that's just using that form here on our photon energy levels, this bit here. So that's what I've done there. And we want to find the kinetic energy, so we're going to rearrange this formula in terms of the kinetic energy. So EK max is equal to HC over lambda minus the work function. But we need the work function in joules, and we're given it in 4.3 electron volts. So this is the information we're given. So all we need to do, convert the work function into joules and substitute all the values in here to get the energy out. So the value for the maximum kinetic energy. Where do people go wrong? It's usually the conversion of electron volts into joules. They'll either not convert it into joules or they'll leave it in electron volts. So that's what we'll do now. So how do we convert joules, so electron volts to joules? So 1 eV is 1.6 times 10 to the minus 19 joules. So this energy in joules, so phi in joules, is going to be equal to 4.3 times 1.6 times 10 to the minus 19. So that gives us our work function, and there's marks associated with that. So there'd be a mark for calculating that. So 4.3 times 1.6 times 10 to the minus 19 gives us 6.88 times 10 to the minus 19. So find the kinetic energy. Let's put everything in. 6.63 10 to the minus 34 times the speed of light over this wavelength. Minus 6.6, so 6.88 times 10 to the minus 19. Okay, we'll bang all that into the calculator. So putting that all in the calculator, can do it all in one step. We want this to 2 significant figures because that's the lowest value of significant figures we have. I get 2.6 times 10 to the minus 19 joules. So that is our value for kinetic energy. Okay, the next question then deals with diffraction. So diffraction and the de Broglie hypothesis. So the matter wave equation. So that is that lambda is equal to h over momentum. So matter has an associated matter wave, and we can observe these effects with electrons. So electrons through an electron diffraction tube, where the electrons diffract through, the usual target is a graphite layer, graphite sheet, graphite target. They're fired on that, and they diffract through the spacing of the graphite atoms, and you get a diffraction effect. Diffraction rings are produced on a screen. This is a show that question. So the electrons are accelerated through a potential difference v, and we need to show that the de Broglie wavelength lambda is given by h over the square root of 2 me e times v. So me, mass of electron, e, elementary charge, v is the voltage. Show that question then. So we can see this is one of those things where you need to put kinetic energy in terms of momentum. Why do we need to do that? Because we've got a mass in there involved. So kinetic energy, we know kinetic energy is half mv squared, and we know that momentum p is equal to mv. Then what do? We can put, if we substitute p mv into that equation, kinetic energy in terms of p would be p squared, because we mv squared, over 2m. Why have I got the 2m there? To cancel out that m squared. So if we write that in there, that's what we'd have. So p squared over 2m. Then what do? We get an expression for this in terms of this relationship here. So we want to try and put this into there. The kinetic energy of the electron can be thought of in terms of the charge on the electron when it's accelerated through a potential difference. So k is p squared over 2m, but this electron is accelerated through a potential difference. So that means the kinetic energy would be equal to Q, which is the charge on the electron, times V, because you can think about it in terms of work being done by this charge moving through a potential difference. So you can imagine this. If you've got plates here, we've got an electron and it's moving there. It's got charge Q and there's a voltage applied. The work done is equal to Q times V. That's where that's coming from. So we can put that into here. So QV is equal to P squared over 2M. So we want an expression for momentum. So P on its own, P is equal to, if we put that over there, 2M QV all square rooted. So we multiply throughout by 2M and then we do the square root to find P on its own. So 2M QV square rooted. Then we go back to our relationship. So lambda is equal to H over P and substitute that in. So lambda is equal to H over P. We've got an expression for P, which is the square root of 2M QV. And if we have it in that term that it wanted it in the equation, Q is a charge on the electron, so we can put that in terms of the elementary charge. So H over the square root of 2M EV, where M is going to be the mass of the electron, so ME mass of electron. So mass of electron times charge of the electron, and that's the expression for 3 marks. So for 3 marks, what do we need to do? Know that momentum is mv, but we need kinetic energy in terms of momentum. And then because the electron is being accelerated through a potential difference, the electron's gaining energy, which is equal to the charge of the electron times by the potential difference. Put that back into our kinetic energy relationship and then rearrange for P. And then finally just write it in the form that it wants it in the question. So that's what we do for that particular bit. So we've done that bit for 3 marks. Okay, final bit then is part B. Calculate the accelerating PD that gives a de Broglie wavelength of 4 times 10 to the minus 11 meters. So B, we need, so lambda is 4 times 10 to the minus 11. Lambda is 4 times 10 to the minus 11. And we need to find V. So we're making V the subject. So make V the subject. What do we need to do? So we'll square both sides, and we'll square both sides because we've got this. Oh, let me just rub that out. So lambda is equal to H over square root of 2 ME EV. Okay, square both sides, what do we get? Lambda squared is equal to H squared over 2 ME EV. So we want V on its own. V is equal to H squared over 2 ME over lambda squared. Now all we need to do is substitute all our values in. So that's why it's 3 marks, because we have to rearrange the equation. So lambda squared, so lambda is 4 times 10 to the minus 11 meters, 4.0, and H we're given, so 6.63 times 10 to the minus 34. Square that. Mass of electron 9.11 times 10 to the minus 31. This is all on the formula sheet. Charge on the electron 1.6 times 10 to the minus 19. Again, that's on your formula sheet. And lambda was given in the formula. and the formula given in the question is 4 times 10 to the minus 11. So that needs to be squared as well. Then just put that all in your calculator. So I like to do the rearrangement first and put values in. I know some other people like to put the numbers in, then do the rearrangement. Either way is fine as long as you get to the answer. So put that one into your calculator. We want this to two significant figures again. So I get 940 volts.